Okay, it's our old favorite. It's the balanced rod. This is an equilibrium. It's really interesting. These questions, you see more questions about moments and balance things in paper 6 than you do in paper 4 and even paper 2 as well. So it's kind of an interesting point here. Anyway, I hope you've done the question. Let me know if you've got any questions as we go along. Okay, and feel free to pause if you haven't done so. I'm going to get cracking on with an explanation right now. Okay. So we've got our meter rule, we're balancing at the pivot, we've got a ball and an object. Okay, now usual story, we've got lots of sort of bits of information here that oh sorry, my screen's being really slow. You don't really need to know. Okay, you're placing the object W at a distance P from the 0 centimeter end. Okay, and we've got a ball here. Red flag here, it's the ball. And we'll come back to that later. Okay, now we've got object W on the meter rule as seen above, as seen from above. Okay, and we're going to make some measurements, usual story. We're going to record the reading at each side. So we're going to pretend we are the student. Okay, now on the left-hand side, we've got 29.5, 29.6. On the right-hand side, that's a bit harder. We're going 31, 30.9, 30.8. That's where our 2 data points come from. I mean, whilst I look at this is a kind of a one that jogs a few memories. Sometimes you get asked, well, why is it difficult to do this experiment? One thing that's difficult about this experiment is identifying the center of your mass, okay, where it's lying. The only thing we can really do is say where the 2 sides are, okay? So this is it's a criticism of this experiment because it blocks the meter rule. By putting the mass on the meter rule, according to my experience, I've never seen a see-through mass for this kind of experiment, and it's going to block the reading. So we can just calculate where this thing is. We don't know it. Okay, that's me just going on a bit of a blabber, but it's certainly something which is important. Okay, so we've got our readings. We're going to use them now to calculate it from the distance P. Now what we're going to do is going to say, well, the center of the object is halfway between those 2. So all I have to do is calculate the average of those 2 values, 30.2. You can see that I've gone 0.6 up and 0.6 down from either side, and therefore I've got a nice 30.2 centimeters. Notice again, if the answer was 30, please write 30.0 because that is a point here you're measuring to the nearest millimeter. Okay, we're going to measure the mass. Now, this is one of those kind of funny ones. You're just basically told, calculate the mass. There's no thinking here. A lot of students might think that P is a rho, and they sort of wonder, why am I dividing here? Okay, just follow the instructions. That's all fine, okay? We've got our 1550 divided by 30.2. Now notice here, this is actually 3 significant figures, okay? 3 significant figures. So we're dividing by 3. We're going to present our answer to 3 significant figures. Generally, if you go on to something like IB or A level, you'll learn that we always present to the least number of significant figures. So if we're calculating and using a number to 3 significant figures, we'll use that in our answer here, 51.3 grams. Now, a difficulty that the student has, we said it before, red flag, it's a ball. The ball might move. Okay, and actually the mass might move as well because we don't know if it's stuck down, but certainly the ball would be difficult to position. That is my biggest thing. Because when you imagine trying to balance this experiment, I give you a ball, I might do this to my students one time, right? Try and get them to do it. You would have the ball flying all over the place, okay, as you try and balance that ruler. The ball might move, and therefore you're not able to take any data. Okay, let's scroll through and see what else we've got. Aha, seen this before, it's a common thing. We've got a mass balance given to 0.01. We're going to record the reading to the nearest 0.1. That's rounding up. It always seems to be rounding up, interestingly. I don't know why that is. Okay, CIE seems to like making people round up, not round down. That's fine. Okay, we're going to go 54.68. That's 54.7. Now again, I've said this a few times when I read these questions, that usually a lot of students find a lot of these points fairly easy. We're doing a bit of data analysis, a bit of data entry, sorry, a bit of talking about experiments. This question that I've highlighted here, part 2, is the tricky one. Because students are a bit confused by this 10% thing, especially because this is new for CIE. They are now telling you that 10% is the golden number. Okay, so we've measured the mass already. We measured the mass, I think, to be 51 point something, 51.3. Okay, and now we're going to compare the mass from here to that value that we measured before, or calculated before. Okay, and what we're going to do is we're going to try and explain whether our values of the mass are considered equal within the limits of experimental error. Now, what the goodness does that mean? Well, they've told you. It's 10%. They have to be a difference of 10%. If it's less than 10%, it's equal. If it's not less, or it's, in other words, greater than 10%, then they are not equal. All right. Now, in this case, this is one of the rare occasions recently, anyway, I found that they are within 10%. If I find my 54.7, take away 51.3, divided by 51.3, gives me 6.6%. Okay, which is less than 10%, so they are equal. You are expected to make a statement, something like that. Okay, we've got a 6.6%, less than 10%. It's not enough just to write, to do the calculation. That would be 1 mark. However, you're then going to go back and calculate our percentage difference. In this case, it's less. The worry I have is if someone calculates 9.9% or 10.1%, even 11%, it's very close to 10. So I just think these numbers are almost always going to be very close. If you get a close number, just justify it. It's okay. If it's greater than, then just say they're not equal, and if it's less than, say they are equal. That's fine. Okay, let's have a look at the rest of the question. Oh, we do another different balancing experiment. Okay. The student fixes an object to one end of the ruler, places the mass of 20 grams. Okay, moves the mass and repeats the procedure. Okay, here's a really good question. The results show that the mass is inversely proportional to the distance of the mass. Okay, and it asks you to explain how. Now, I've not seen many of these, and so I think it's a really good one. Okay, let's have a look. We've got some lovely data, and what we're saying is that this and this are inversely proportional. Now, what that means is if I double the distance, double the mass, I'm going to halve the distance. Hopefully you can see that. If I go from 20 to 40, that halves to 12. 24 halves to 12. 40 to 80, 12 halves to 6. So it's nice. And you could actually just write that down. I think that would actually be fine. You could notice that doubling if we go from 20 to 40, 24 becomes 12 divided by 2. Okay, you could then do that from multiple data sets. Another way of saying that is that when you multiply them together, you get the same value. It's the same thing. You notice here, okay, I think I made a little numerical mistake there. Whoops, I'm missing a factor of 10. Whoops. 20 times 24, okay, should be 480. All right, and then that's the same here as 6 times 80, 480. They balance, you wouldn't lose marks here. Okay, so basically the numbers multiply to be the same. If you want things to be inversely proportional, they multiply together to make the same number. You don't need to explain why, you just need to be aware of that. You could also explain it using that idea of halving, double M halve D. That would also work. Okay, now we're going to try and think about confidence. Now this is quite interesting. Again, I've never really seen this before. It tells you how can we make ourselves more confident about this relationship, but do not tell us to repeat the readings, right? What they're saying here, and this is examiner code for, well, you guys keep on telling us the best thing to do is average. We've heard that many times, so we're well aware that that's a good thing to do. What else could we do? If I look there, okay, I thought this was a good one, okay, I would suggest using a wider range of data, okay, because you've got 4 masses, okay, now 4 masses is good, but we want more because the more data points we have that confirm this relationship, the more we believe it. So if you want to increase confidence, you would do this for a wider range. Really what you would do is you would just do it for another data point that's much, much bigger or much, much smaller. So for example, if you change that next data point to 200, 250, 500 grams, it'd be really interesting to see if that still holds, okay? And that would be allowing a much wider range of results. Now, obviously, don't go daft. If you said mass was 1,000,000, that would be also very silly, okay? So just saying that it's a wider range or more values is probably completely sufficient here.